Okay? Okay, we can start. For good now. Prima le signore...
Le lezioni iniziano alle 9, perché tutti ancora entrano alle 9:09?
sì, beh, anche noi siamo arrivati un po' di ritardo, eh? Okay, so let's continue with the basic notions, notations actually. We were defining the notation for the spinors, right? Gamma 5, the gamma 5 matrix is defined as I over 4 epsilon mu nu rho sigma gamma mu nu rho sigma, which is also equal to I gamma naught gamma 1 gamma 2 gamma 3, and you can verify in our representation that this is nothing but the 2 by 2 identity plus the identity 0 0. Okay. Okay, then spinors. Spinors can be described in as a 4-dimensional vectors made of Grassmann numbers, chi, and they're written in the following form, okay, using the two-spinor notation. They consist of an upper component consisting of a two-component spinor and a lower part consisting of another two-component spinor. Okay? We call in a different way the two indices, alpha and alpha dot. They run from 1 to 2. Okay? This is the Sonius notation, but it's broadly used, widely used. In this notation, zeta bar alpha dot is zeta alpha star. So the effect of star is to bar this quantity and turn alpha into alpha dot. Then we use the northwest southeast convention for raising and lowering indices with the epsilon symbol. Okay, epsilon symbol is important because it's in SU2 invariant. Epsilon alpha beta is the matrix 0 1 minus 1 0. Northwest southeast means that zeta alpha is equal to epsilon alpha beta zeta beta. Okay, so the free index, okay, the free index when it's upper, okay, in the upper position, okay, is to the west, so northwest. When it is in the lower position, it is on the left, on the right, sorry. So southeast, northwest, southeast. This is just a convention, okay, for raising and lowering in indices with the epsilon symbol. This is the convention we are going to use. So it's important to fix the conventions. So, for instance, if we have two B-spinors, like this, and we contract them like this, okay, this means that there is an epsilon symbol contracting them, right? In particular, there is this, we can write it epsilon alpha beta 1 beta 2 alpha, okay? You can easily verify that this is equal to minus psi 1 alpha, psi 2 alpha, okay? Why do we use this notation for the four spinors, right? Where these indices in the lower and the upper position. Well, the reason, the basic reason is that the spin operator acts in the same way by means of the same matrices on the upper and lower components. You can verify, and I invite you to verify it, that the spin matrix, okay, the spin operator, which is I epsilon I j k d L j k divided by 2, this is the definition we gave yesterday. If we replace the spinor representation here for the Lorentz generators, okay, we simply get 1 over 2 sigma I, where sigma I are the Pauli matrices. So the spin acts by means of the same matrices on the upper and lower components. This is the reason why we use this notation here. Okay. Okay. We have defined the. So if we have two spinors, right? If we have one spinor in this form here, we can compute its Dirac conjugate and its charge conjugate. The Dirac conjugate of psi, you can easily verify, that is psi dagger gamma naught, and this is equal to zeta alpha, where zeta alpha is just the star of this, okay? Psi bar alpha dot, right? Now we can compute also the charge conjugate of psi. Remember that C is I minus I gamma 2 gamma 0, gamma 2 gamma 0, and it is a matrix of this form here. Is minus epsilon alpha beta and epsilon alpha beta, okay, 0 0. It's real antisymmetric, okay, and it coincides with minus its inverse. So if you apply the definition of charge conjugate, you find a vector like this. Okay? Okay. Now, a generic spinor is reducible. Okay, we can impose the Majorana condition. Majorana in 4 dimensions. Majorana spinor. Majorana spinor is a spinor which coincides with its charge conjugate. Okay? What does this mean? This means that zeta alpha equals psi alpha. Okay? So a generic Majorana spinor has the form psi alpha, psi bar alpha dot. Okay? So the upper and lower components are related by charge conjugation and multiplication by the epsilon symbol, right? You can easily verify that this is Majorana. If we have 2 Majorana spinors, we can contract them, okay, in a Lorentz invariant form, like chi1 bar chi2 to Majorana.
Can you just clarify what the spinor is?
Sorry?
Those letters were
Oh, sorry. This is psi. These 2 letters are the same. I'm sorry. It's Greek letters, so I'm not very good with the Greek letters, but there are two symbols basically. One is xi, this is xi, and this is zeta, and they are different letters, okay? But in Majorana spinors, okay, the two coincide because of the Majorana condition, okay? So the lower component is actually the star of the upper component multiplied by epsilon. Okay. Okay. North-west. Okay, when the free index is in the upper position, okay, it stands on the right, on the left. Northwest. Southeast when it's in the lower position, right? Okay. So this can be written, we just recall this expression here. This can be written as xi1 alpha, xi2 alpha, right? Plus xi1 bar alpha dot, xi2 bar alpha dot, right? This is the expression of the Lorentz invariant contraction between two Majorana spinors. Okay? Remember that if we lower here alpha and we raise alpha there, because of our conventions, we get a minus sign. Xi1 alpha, xi2 alpha with a minus sign. The same happens here. Minus xi1 bar alpha dot, xi2 bar alpha dot. But then the spinor components are Grassmannian numbers. So you get a minus sign if you switch their position. Okay? So xi2 alpha, xi1 alpha, plus xi2 alpha dot, xi1 alpha dot. Okay? But what is it? What is this? This is nothing but xi2 bar xi1. Okay? I wanted to check if you were following. Very good. Chi2 bar chi1. Okay? Thank you. This is just for Majorana. Okay? In general, for non-Majorana, you have the following properties which you can easily verify, but which are useful when you do calculations. They're all in the appendix of my lecture notes. Okay? So, first of all, it's important to define the symmetry of the following matrix, okay, which is obtained by multiplying C times this antisymmetric product of gamma matrices. C, gamma mu1 mu k. You can easily verify that the transpose of this is equal to minus k plus 1 divided by 2, C, the same gamma matrix. Well, the same quantity. Huh? Okay. Next, chi bar C gamma mu1 mu k. So here we are dealing with non-Majorana spinors, okay, because I'm using C here. Okay, non-Majorana spinors. You can easily verify the following. Minus k plus 1 divided by 2 lambda bar C gamma mu1 mu k chi. This you can verify, check. And also that chi bar C gamma mu1 mu k lambda star. This is also something which occurs frequently in the calculations. This is minus k chi bar gamma mu1 mu k lambda C. Okay? You can check these. And you see, for k equals 0, what do we get? For k equals 0, we get chi c bar lambda equals, well, star, equals lambda, or chi bar lambda c, and this is 1. The other thing here, for k equals 0, from this one, we get a generalization of the property we just derived for non-Majorana spinors. Generalization of this for non-Majorana spinor. We get chi bar lambda for k equals 0 is equal to lambda c bar chi. Okay? That you can easily verify. K equals 0. And then if the two are Majorana, then you just delete the c and you get our previous property. Okay? Any questions? These are just notations. You can easily verify and find them out on any books. Given a generic spinor, okay, for spinor, we can define its chiral components. How? Well, we define a chi upper bullet, which is 1 minus gamma 5 divided by 2 chi, and chi lower bullet, which is 1 plus gamma 5 divided by 2. This is equal to psi alpha 0, and this is equal to 0, times chi, clearly, 0 zeta bar alpha dot. Clearly, we define it for generic vectors, okay? Not necessarily, generic spinors, not necessarily Majorana. This is just these are just the chiral components of the spinor. Okay. We are now ready to write down the supersymmetry algebra and then to discuss its representations, right? This is what we're going to do today. So, when was supersymmetry introduced? Well, supersymmetry was introduced a long time ago, okay? Before people even realized its possible applications to particle physics. Okay, it was just a mathematical thing at the beginning. Okay, a symmetry between fermions and bosons. Neveu, Schwartz, and Ramon. It was in 71. Then Golfan, Lichtmann, 71, Wess-Zumino, in 74, and Volkov, Akulov, in 73. Volkov, Akulov, actually, they defined a nonlinear realization of supersymmetry, okay, which now it's is attracting a lot of interest in various contexts, okay. So supersymmetry, super Poincaré algebra is a graded Lie algebra consisting of bosonic generators and fermionic generators. Bosonic generators are L in P mu, okay, and the generators BR of the internal symmetry group. So this is Lorentz, no, Poincaré. And this is G internal. Then we have fermionic. Qi. How do we define Qi using our notations? Well, Qi is a Majorana spinor of generators. So it's defined as a Majorana spinor. In particular, it has an upper component, Q alpha I, and a lower component. Notice the different position of the index I in the upper and in the lower. Okay, this is important because when written in the upper and in the lower, okay, we will see there's going to be a complex symmetry group acting on it, okay, which is going to be manifest in the algebra, okay. And Q, as usual, Q alpha dot I epsilon alpha beta Q beta I dagger, okay, as usual, north, west, southeast. Okay, very good. What are the commutation and anti-commutation relations? Well, the commutation relation between Q and L, well, these are a kind of fixed by the fact that we choose Q to transform in a spinorial representation. So we know that Qi L mu nu, remember how operators transform, okay, this is going to be delta mu nu Qi, okay? So the infinitesimal variation generated by L mu nu, Lorentz transformation on Qi. And this is nothing but gamma mu nu half Qi, okay? Sure.
So the two components in the spinor Q,
Yes.
they are not independent.
They're not independent. No, no, you see. Because the Q is defined as a Majorana spinor. So we choose to work with Majoranas, and any supergravity can be written in terms of Majorana spinors in 4 dimensions, okay? So also Q bar I L mu nu, this is equal to minus Q bar I gamma mu nu half. Then Q commutes with P. This is what we have shown yesterday. Now, the less trivial part, okay, of the structure of the super Poincaré algebra, okay, is the anti-commutation relations, okay. They have this form, Q alpha I, upper component of the, so B spinor, upper component of the generator, supersymmetry generator, times Q bar beta dot J. And here I've lowered beta using the epsilon symbol, northwest, southeast. This is equal to 2I delta ij sigma mu alpha beta dot p mu, okay? So the anti-commutator of two supersymmetry transformation is a space-time translation. Remember, curly p is the generator of the space-time translation. Is related to the 4 momentum generator by an IH. Actually, now we are using HC equal 1. From now on, we stick to the natural units, in which H is equal to C is equal to 1. You should be familiar with this. So this can also be written as twice delta ij sigma mu alpha beta straight p, which is the 4 momentum operator, okay? Remembering that straight p mu is equal to IH p mu, and in our notation is simply I p mu, okay? Then there is another relation here, Q alpha I, Q beta J. What is this? This is twice epsilon alpha beta Zij. Zij is a complex antisymmetric matrix, n times n. Complex antisymmetric, okay? Now, we also have the BR generators, right? Which act on the various fields. Okay, in particular, they close BR, BS is equal to FRSP, BP, okay? These are the internal group. Now, this internal group should act on I, okay, on the index I, and Qi, alpha I, belongs to a representation of G int through the index I. So I defines, labels a representation n of the internal group, okay? But then you have that these generators, okay, these generators, the action of this G internal, okay, on the whole algebra, the adjoint action of G internal on the whole algebra should be an automorphism, an inner automorphism, because it's generated by part of the group, okay, and therefore should leave all these quantities, the structure constants, invariant. Particularly, should leave epsilon alpha beta and delta ij invariant. Okay? But this means that G int should be contained in SUN times U1 to the k. For some k. Right? What else? Well, Zij, what are they? Well, Zij are internal generators. So they are a combination of these. R, BR. They are a combination of these internal generators. Okay, now there is a constraint on this coming from the super Jacobi. Yeah? Sure. By definition, we have said that the spinorial generators, okay, they have one leg along spacetime and one leg in the internal space, acted on by the internal symmetry group. Okay, so it's a spinor. So it transforms in a well-defined representation of the Lorentz group and has an index I. This index I is an internal index. By definition, it is acted on by the internal group, internal symmetry group, generated by P. Okay?
This means that the internal symmetry group is telling me how many supercharges I'm considering? I thought the I index was labeling how many...
Yeah, the I index is labeling the number of supersymmetries. According to the number of supersymmetries you choose, okay, you have different choices of the internal group, clearly. The internal group acts on the internal index of the supersymmetry transformation and reshuffles supersymmetry transformations, right? So this is an input you choose at the beginning. I mean, how many supersymmetries you want in your theory. Depending on n, the number of supersymmetries you choose, you have various choices of this internal group. The internal group transforms, well, acts on this index n, reshuffles your supersymmetries. That's the way it works, right? If I choose one, then I don't have much choice. If I choose two, then I have more choices. It can be SU2, okay, times number of U1s, one U1 basically, okay?
The distinction between the I index done for all has to do, I mean, it depends on the specific group that I'm considering.
Of course, yes, but as I said before, the adjoint action of the internal group on the rest of the algebra should be an automorphism. This imposes constraints on the possible structure of the internal group. Okay, cannot be generic. In particular, what does automorphisms mean? Automorphisms mean that if I transform all the generators by means of this internal group, okay, then it should leave all the structure constants invariant, in particular this invariant. But this implies that your internal group has to be a CUN times U1 to the k, a number of. Also Z are not generic, okay, they are internal, so they have to be a combination of this B, right? Okay. We know that the structure constants of a Lie group, of a Lie algebra, okay, they should satisfy Jacobi identities, okay? Also here we have Jacobi identities. However, they are, we are dealing with a graded Lie algebra, so Jacobi identities have a slightly different form. In particular, let us define TA, generic generators of graded Lie algebra. Okay? And let us define a hybrid commutator like this. This is an anti-commutator if TA and TB are fermionic. A commutator otherwise. Otherwise. Okay? This is the notation, just a shorthand notation. Super Jacobi, you can verify that TA, TB, TC plus graded cyclic permutations of these three generators has to be 0. That you can verify explicitly using the definition of commutators and anti-commutators. Okay? What do we mean by graded cyclic? Well, graded cyclic means that if the cyclic permutation involves interchange in the position of two fermionic generators, you get a minus, right? So for instance, if you have Q1, L, Q2, okay, this is a fermionic, so this is going to be an anti-commutator, okay? Then we have another thing here, which is L, Q2, Q1. This is bosonic, so this is going to be a commutator, okay? L is the bosonic, a generic bosonic generators. But here, should we put a plus or minus? You see, in this sequence, the order of the two fermionic generators is inverted. So I need to put a minus here, right? And then here we put a Q2, another minus here, Q2, Q1, L. Okay? Because also here, with respect to this order, the order of the two, this sequence, the order of the two fermionic generator has been inverted. And this has to be 0. Okay? So this is the meaning of graded cyclic permutation. Okay? Now, this condition imposes constraints, as usual, on the structure constants. Okay? And in particular, you can verify that this implies that Zij are central chargers. And I invite you to do the computation. Zij has to commute with everything, with all the other generators. Okay? So this means that Zij belong to, or generate the U1 to the K of the the U1 to the K part of the internal symmetry group. They have to be there. Okay? And then what else? Well, the B's should also leave Zij invariant. Zij, they transform in the n times n representation of the internal group, should leave Zij invariant because Zij should commute with anything. Okay? This is a constraint on the internal group, and that tells us that the internal group should be actually contained in the group USP n times U1 to the k. Okay? This is the freedom we have, USPn. This comes from the fact that we require the internal symmetry group, okay, to leave Zij, which is an antisymmetric complex matrix, invariant. Okay. We can use a four-spinor notation for writing the anti-commutation relation between two supersymmetry generators. Okay, if we write the anti-commutation relations, we can write them like this, where now these two are four spinors. These two are four spinors. And you can verify that this is equal to 2i delta ij gamma mu. We are dealing now with four spinors, p hat mu plus a matrix plus 2i, a matrix z mu, zij, where zij now is a matrix, also is a 4x4 matrix for each value of I and j. For each value of I and j is a 4x4 matrix acting on spinors. And it has this form. If Zij is the complex matrix, which we write in terms of a real part and an imaginary part, like this, then Zij, it's I times Rij, gamma 5, plus Iij, times the identity, 4 times 4. That I invite you to prove, okay? That the central charge in this four-spinor notation enters the anti-commutation relation in this form here, as a spinorial matrix for each entry ij, right? Okay. Any question? Okay, this is enough about the supersymmetry algebra, but what can we say about the automorphism of the algebra? Okay, an algebra can have inner and outer automorphism. Inner, if the automorphisms are produced by group elements generated by the algebra itself, okay? And their action on the generator is the adjoint action, is the conjugation, right? Or outer, if it is induced by transformations which are not in the group generated by the Lie algebra, okay? In particular, there are transformations which are not in the group. There are transformations which are not in the group. Okay? But nevertheless, which are in the supergroup, super Poincare group, but nevertheless, which are automorphisms of the algebra. Namely, they leave the structure constants invariant. If TA is mapped into T prime A, then TA TB equals CAB C TC implies that the transformed generators simply close the same superalgebra. Let's use this. Okay? They close the same superalgebra, same structure constants. Okay? In particular, you see that if we transform Q's by means of a n times n matrix, complex matrix, so if we transform Q alpha I in Q prime alpha I equals U I J Q alpha j, and therefore Q alpha bar alpha dot Q bar alpha dot I Q prime alpha dot I, which is equal to U I J star Q bar alpha dot j. Okay, there is a star here. Remember that these two are related by a charge a conjugation, Hermitian conjugation. Okay, and Zij goes into Z prime Ij, which is equal to Uik Ujl Zkl. So you simply transform by means of this matrix U all the indices I. The algebra is invariant provided U belongs to Un. Why is it so? Well, because of this condition here. You do this transformation here, okay? Then the matrix U and its star will act on delta. But U is an automorphism only if it leaves the structure constants, like this delta, invariant. But this implies that U dagger has to be 1. So in order for this transformation to be an automorphism, namely to leave this delta invariant, it has to be unitary. Okay? Don't mistake this group here for this internal group, the internal group that we wrote. Okay? Internal group is part of the super Poincaré group. Okay? This is an automorphism, something which acts from the outside but leaves the structure constants invariant. This is called R-symmetry group. So the automorphism group of the Poincaré algebra, the super Poincaré algebra, acting on the index I, is called the R-symmetry group. And it is UN. Call it GR, R-symmetry, and it is UN in general. Okay? We will see that for certain representations, this group is broken down, okay, to SUN for certain representations. Okay? But this is the most general automorphism group acting on the index, internal index. Clearly, UN is not manifest if we work with Majorana spinors. Why? You see, Qi alpha I transform in the representation n of UN. Q bar alpha dot I, it has an upper I, transform in representation n bar, and the two are different, inequivalent, unless n equals to 2, okay? But the two are inequivalent, okay? And if we merge them inside a single vector, single spinor, then we are losing the manifest UN transformation property, because we are putting together things which transform differently. We are putting together things which transform differently, one in the n and the other in the n bar, okay? So we are losing manifest UN symmetry, but it is there. That's why it is useful to write down the superalgebra in the two spinor notation, okay? Because there, in this two spinor notation, UN is manifest. there is a way in which to make UN manifest also when you deal with Majorana spinors. Okay, how do you do that? Take a matrix U in UN. A unitary matrix, you teach me, is the exponential of an anti-Hermitian matrix, right? Anti-Hermitian matrix. So U is the exponential of an anti-Hermitian matrix, but an anti-Hermitian matrix is an antisymmetric real matrix plus I a symmetric one. A plus IS, okay? Then Q alpha transforms with U, Q alpha acting on the index I, Q alpha dot transform with U minus 1 transpose, Q bar alpha dot. Okay? But what is this? This is equal to e to the a minus is Q alpha bar dot. Okay? So Q transform, the upper two spinor, transform with the exponential of a plus is, the lower with the exponential of a minus is. The two together, qi, which is q alpha, I q bar alpha dot I, they transform with a bigger matrix, U, which is a 4 by 4 matrix. Sorry, not 4 by 4, but 2n times 2n matrix, 2n times 2n matrix, which is e to the a plus is acting on the upper components and e to the a minus is, 0, 0. But believe me that you can easily check this is nothing but exponential of a times the 4 by 4 spinor index acting on the spinor indices, spinor matrix acting on the spinor indices, minus I s gamma 5. Okay? And this way you can make UN also manifest. Well, this describes the action of UN on Majorana spinors. You have to include also gamma 5. Okay? A and S act on the ij indices. Okay? Identity gamma 5 on the spinorial index, on indices, right? So this U matrix, this actually should be thought of as a matrix acting on both internal and spinorial indices. Okay. Okay, so representations. Are you tired? No. Okay, representations. Well, let's just start, and then I give you 5 minutes break, okay? So, as we said, representations. Q commutes with pi p squared, and therefore all states in a given representation have the same mass, but they have different spin. But different spins. Okay. Another important thing that's very important about globally supersymmetric theories is that the existence of the presence of this of the super Poincaré group as a symmetry, okay, of the theory, that is the fact that they have a super Poincaré group as a symmetry of the theory, implies that the energy of the states cannot be negative. So implied, it gives a principle of positivity of energy, okay? Implies that the energy of the states cannot be negative. Why is it so? Well, that follows directly from the anti-commutation relation, Q alpha I, Q bar beta dot J, upper J, that which is equal to twice delta ij sigma mu alpha beta dot straight p mu. Here I'm using straight p, the 4 momentum. Okay, not just a translation, but the 4 momentum, so this means that there's no I here, right? 4 momentum. Good. What we can do is we can sum over alpha and beta, okay? We can equate alpha and beta dot and sum over them. Let's sum alpha 1 to 2, Q alpha I, Q alpha dot, which have the same value, J. And what is this? Well, here I'm tracing these matrices, right? But the Pauli matrices corresponding to the space values of mu, they're traceless. So the only matrix here in this sum which contributes is a 0 matrix, which is the identity. Okay, so what we end up here is 4 times delta ij times the 0 here. But the 0 component of P is the energy operator. This is important. Okay, so take a state now, a state A, and sandwich this, operate both sides, okay, on this state A, namely compute the vacuum, the expectation value of both these operators on this state. A this is the VEV of the energy, the vacuum expectation value of the energy. Okay? Now remember that this operator is the dagger of this one. Remember, Q alpha dot I is Q alpha I dagger. Okay? This is important because what is this? The right-hand side. For I equal j, what is the right-hand side? Take I equal j, any from 1 to n, any index from 1 to n. This is nothing but, well, A, Q alpha I, Q alpha I dagger, A, plus the term in which the two are interchanged, okay? But this is nothing but, you see, the squared norm of Q alpha I dagger A, okay? Okay, so the right-hand side is nothing but sum over I, sum over alpha from 1 to 2 of what? Of Q alpha I A squared plus Q alpha I dagger A squared. And this is equal to what? This is equal for any I, because I is a free index, is equal to this vacuum expectation value, 4 times A H hat A, okay? I've just rewritten the left-hand side of this, okay, as a sum over sum of squared norms of states in the Hilbert space of states. Now, under the reasonable assumption, okay, that the norm on the Hilbert space of state be positive definite, okay, at least not negative, not indefinite, because we want the norm of physical states to be positive, okay, or positive definite at least. This implies that this has to be greater or equal than 0, because the vacuum expectation value of the energy on any state cannot be 0. Cannot be negative, sorry. Can be in general is greater than 0 or at most equal to 0, but not negative. Cannot be negative. So this gives us a principle of positivity of energy. If our theory has an underlying super Poincare symmetry, energy of any state has to be positive. Okay. Among all the states, we can choose the vacuum, okay, of the theory, the vacuum of the theory. Now, that is the state with the least energy, the least energy, the vacuum of the theory. This applies clearly also to the vacuum, okay. Now, what we see here is that if the vacuum is supersymmetric, namely it preserves all supersymmetry, supersymmetric means that it is annihilated by all the supersymmetry generators, so Qi not equals 0, okay, and Q bar as well. Well, what does this imply? This implies that also the energy of the vacuum is 0. So if the vacuum has a positive energy, supersymmetry is broken. If we find the vacuum with positive energy, then this means that supersymmetry is broken. Okay? Now there's another thing which we can learn from here, okay, which is instructive and is also false. But let's have a look at this. Suppose that the vacuum preserves just a fraction of the n supersymmetries, not all of them, like here, but just a fraction, okay? Namely that there exists a number, just a number, say 1 supersymmetry, I equal 1, which annihilates the vacuum. Okay, alpha 1, 0 is equal to Q bar alpha dot 1, 0, and this is 0, suppose. Okay? What does this mean? Well, this equation holds for any I, and therefore also for I equal 1, because I is a free index there. So this implies that the energy of the state is 0. Okay? But then, this holds for any I. This implies that also the norm of the states obtained by acting on the vacuum by means of all the other supersymmetry generators have to be 0, because this is a sum of squares. And it has to be 0 for any I. If it is 0 for one I, you see, it has to be 0 for any I. Okay? So this would imply that Q alpha I be 0. So it seems that we cannot have a partial supersymmetry breaking. Either we break all supersymmetries, or none. Seems to be an obstruction in having a partial supersymmetry breaking. Okay? This is an argument which was originally put forward in the 70s, but then it was evaded in the 80s. The argument is a bit subtle, okay, because this seems to be quite strong, but the argument is a bit subtle because in local field theories, the correct way of describing symmetries, okay, is in terms of symmetry currents. Okay, so local relationships, because the local field theory is defined in terms of local quantities, and in particular, therefore, also symmetries are defined in terms of local quantities. What are these local quantities? The Noether currents. Noether currents are local. They are defined on solutions of the theory. Okay, they depend on x mu. They are local. Okay, the correct way of describing symmetries is not in terms of commutation relation between Noether charges, but in terms of transformation properties of the Noether currents local. Okay, and indeed you can work out in supersymmetric theories the Noether current associated with supersymmetries. The Noether current has the same indices, but one index more, a space-time index. Q is obtained by taking the zero index and integrating over the volume. Okay, this is the definition of Q. As usual, no, Noether charges, Noether currents. If we write down the anti-commutator relation between a supersymmetry generator and the Noether current, the supersymmetry Noether current, what you end up with is a local, let's write alpha dot, local relationship, okay, in which here nu, you have T mu nu x, okay, the energy momentum tensor. Now you take the mu equals 0 component of this relation, you integrate over the whole volume, and you end up with the anti-commutation relation between supercharges, okay? So this is the local version of our supersymmetry algebra. Local version depends on x mu, okay? Now this is the correct way of describing the symmetries of a local field theory. And you see here, this there is also a delta IA. This relation can be deformed by adding a new term. Plus sigma mu alpha alpha dot Cij. We can add a C number. This is just a number, a matrix made, n by n matrix made of numbers. While T contains creation and annihilation operator because it's expressed in terms of the free fields, also J and Q, C is just a number, but you can add it. This is the freedom you have. That amounts to shifting the energy density by a constant. But a constant which depends on the direction in the supersymmetry algebra. This is a freedom you have. This is a freedom you have. Because the theory is not coupled to gravity. So you can take the energy density and shift it by a constant, and nothing happens. It's unphysical. Okay? But you can do that. You can do that. And what happens is that this term here allows you to evade the no-go theorem just mentioned and to have partial supersymmetry breaking. Okay? So the first model featuring partial supersymmetry breaking, rigid supersymmetry breaking, was constructed by Antoniadis, Partouche, and Taylor in 1996, if I'm not wrong, okay, or 5. Antoniadis, Partouche, and Taylor, and the Taylor, okay? And in this model, Cij was different from 0. But what happens is, so this Cij, being a C number, it has trivial action on any field. So it's really a central extension. It's a central extension. But what happens if you integrate this over the whole volume? Well, if this is a C number, is a constant, you integrate it over an infinite volume, you have infinite. So this shows you that in theories with partial supersymmetry breaking, the anti-commutator between charges is not well defined, is infinite. So the correct way of describing symmetries is through the symmetry currents, okay, and their transformation properties. Local relationships. Okay, let's have 5 minutes break, and then we go on. So we are now discussing irreducible representation. V is the space of the representation, namely space of states on which the super-Poincare group X, okay, it splits on bosonic into a bosonic and a fermionic subspaces consisting of bosonic and fermionic states. If we act by means of Q supersymmetry generators on bosonic states, we end up with fermionic states, so subspace of this F, Bf, and if we act once again, okay, on such states, we end up with bosonic states, okay? So the double action of Q on VB is contained in VB. Two consecutive supersymmetry transformations on a bosonic state gives us bosonic states. Fine. But this space here, obtained through the double action of supersymmetries on bosonic states, this guy contains also states acted on by the anti-commutator of two supersymmetries. States like this. Okay, acting by means of the anti-commutator of Q, two Qs on VB. But this is equal to basically P times VB, symbolically speaking, okay? Namely, this amounts to the action of the space-time translations on VB, okay? Now, on linear representations or realization on fields, local fields, okay, P has a free action, okay? Take a field, translate it, you get an action, a non-trivial action, a different dependence on space-time, a different field, okay? So P has a free action, namely there's no state which is invariant under the action of P, okay? As a consequence of this, the kernel of P, of the operator P, is trivial, consists of the only null state. Okay, this means that P is injective.
Can you repeat argument?
Yes. On representations on fields, okay, linear realizations on fields, linear realization of fields, the action of P is always free. Free means that there's no field which is left invariant. If I take a field, phi x, and I act by means of a space-time translation, I get phi x plus delta x. It changes. There's no field which is left invariant by the action of P. This means that P is injective. P is injective, and this means that the dimension of QQ VB has to be equal to the dimension of VB. Okay? The dimension of the image through Q times Q of VB is equal to the dimension of VB. Okay? But this implies that this is also equal to the dimension of VF, which is in the intermediate step. Okay? So this implies that in a representation, linear representation on fields, linear realization on fields of the super Poincaré group, dimension VB equals dimension VF. Number of bosonic states equals number of fermionic states. And this is important. However, remember, these states are always considered on shell. Because also when we construct irreducible representation of the Poincaré group, we impose the on-shell condition, p squared equals m squared. Okay, so all these states are on-shell. The states we are constructing are on-shell, and this equality holds on shell. Okay. Yes. 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 True, but that is basically that corresponds to the null state, basically. So that corresponds really to a null state in that case. So we are here basically. So a constant field is really a field which has no dynamics. Okay. How do we construct representations of the super Poincaré algebra? Just as we do for the Poincaré group. Okay, we go to a particular reference frame, S naught, particular reference frame in which P in which the form momentum is simplest. Okay, as the largest number of component vanishing. Okay, P is simplest. Then we construct all possible states in this representation. Okay, using our acting on a given state by means of the generators of our algebra. Okay, and then once we have all possible states in this representation, okay, we construct in this reference frame. We construct a generic state in any other reference frame by simply using the Lorentz boost. By means of the Lorentz boost, I can go from P mu to P using a specific Lorentz generator, a Lorentz boost. Okay? And then we move from S naught to a generic S. And so we construct the whole space V of states of the irreducible representation. So first we construct an irreducible representation in S naught, okay, all possible states of the system in a given reference frame, and then we boost them, okay, to construct the generic state on a generic reference frame. Clearly, to construct the generic states in a fixed reference frame, we cannot act by means of all generators or transformations in the super Poincaré group. Why? Because there are transformations which would alter the reference frame, the boosts, okay? That would take me out of my reference frame. I don't want to act by means of these, okay? So, to construct all possible states in a given reference frame, I can only act by means of the subgroup of the super Poincaré group, which leaves S not invariant. That is, which leaves P bar invariant. This is called the little group of P bar. Okay? I can only act by means of those super Poincaré transformations which leave this particular choice of momentum invariant. I act by means of these transformations on a given state. I construct all possible states in S naught. Then I boost them. So I get to a generic reference frame. Okay? This is the strategy, this is the method of induced representations. This is the method of induced representations. This is the method which is followed, generally followed in any textbooks of field theory, okay, to construct irreducible representations of the Poincaré group. But the same method is used to construct irreducible representations of the super Poincaré group. We need to know what the little group is. The subgroup of the super Poincaré which leaves P bar mu invariant. That depends. We are on shell condition, okay? That depends on the mass of the particle, okay? If the particle is massless, okay, then we can choose as standard for momentum, P bar, a vector of this form here. And this is equal to P naught, and minus P bar, okay? Minus P. Minus because mu is lower, okay? This is the best we can do. This is the best we can do because we cannot really set all the internal momentum to zero, all the space momentum to zero, okay? So this is a momentum, this is momentum describing the massless particle, like the photon, okay, moving along the third direction, z-axis, okay? And what is the little group? The little group is SO2, acting on the transverse directions, SO2, and this is the helicity generated by the helicity operator gamma, okay? But we also have the supersymmetry transformations, since supersymmetry transformations will leave P invariant, okay? So in the little group we have to consider also supersymmetries, okay? Supersymmetries will not alter our reference frame, okay? So let us start with the massless case. For massive particles we can choose the reference frame, okay? So the rest frame as a reference frame. So P bar mu equals to M000, rest frame, okay? In this case, the little group is SO3, which is locally isomorphic to SU2, is the spin group, okay? And also SUSY, supersymmetry transformations, okay? Okay, so let's consider the massless case first. Massless case first, M equals 0. We have the Pauli-Lubansky generator. I hope you know that. This is this case is simply P mu times gamma, gamma being the helicity generator. And the helicity generator, this is equal to P, well, the VEV of, no, the VEV, the expectation value of the helicity generator, this is equal to P bar expectation value of the spin generators, okay, divided by the modulus of, that's the usual definition of helicity generator. In this case, it is nothing but J3 in our specific reference frame. Yes?
Why are we considering just SO2 instead of ISO2 for the little group of
Yes, because ISO usually, this is standard in the construction of these representations. ISO2 consists of SO2 plus 2 nilpotent generators. Now, if you assume these nilpotent generators to act non-trivially on the states, you're going to end up with infinitely many states. You don't want that. You want your system, your particle, single particle system, to be described by finite number of states, okay, in the reference frame S0. This means that you have to impose these translations to be trivial on your physical states. That is, to annihilate your physical states. Otherwise, you can show that you can produce infinitely many. So your system would have infinitely many internal degrees of freedom. While we know that the spin degrees of freedom, the helicity states in this case, have to be finite. Okay, this is standard in. Yes.
The ISO2 instead of just SO2, shouldn't it be like a signal of some gauge symmetry arising? That is the infinitely many states.
But you don't want a gauge symmetry. I mean, that is you want a spin group, right? You want a group which describes your spin degrees of freedom of the states. So you want finitely many states. Infinite states for a single particle is too much. It's too much. This is why this is why the action of these extra nilpotent generators have to be zero. It's not about the gauge symmetry. This is not a gauge symmetry. Okay. It's not a gauge symmetry. This is the spin of the particle, right? It's discussed on in the Weinberg book. This issue here. Okay. Yes. It takes ISO2, but then the nilpotent generators are zero. Check. The nilpotent generators are zero. Otherwise, you'll have a system with infinitely many internal states, and that's not cannot be the case. It's not about gauge symmetry. Okay, this is really spin group. Okay. So states in S0 are eigenstates of this of gamma of the helicity generator. Okay. In particular, we can write those states as plus or minus S, E plus or minus S. Okay, where gamma, E plus or minus S, is equal to plus or minus S, E plus or minus S. Okay, where S is the helicity of the state. Okay, so W, the Pauli-Lubansky zero component, E plus or minus S, is equal to E times plus or minus E times S, E plus or minus S. Okay. Now let's evaluate the commutator between supersymmetry generators and the helicity operator. We know that Ji, the rotation generators on Q, I, that is equal to minus SI And this is equal to minus sigma I half qi. Okay? Remember the representation of the spin generators on this. This is the algebra. This is the algebra of the super Poincare group. Okay? So in particular, gamma, the helicity generator on qi, is nothing but minus sigma 3 divided by 2 qi. Okay? And it does not depend on the upper and lower components. Because for our choice of notations, the spin generators, they act by means of the same matrices on upper and lower, provided the upper have a lower index alpha and the lower have an upper index alpha dot. Okay? Okay, then let's see what is the effect of the action of Q on a generic state. If I take a generic state E lambda with helicity lambda, and I act by means of Q I on it, okay, what do I get? Well, let's act on this state, transform state by means of gamma, and let's write this as a commutator of gamma Qi plus Qi gamma E lambda. Okay? But this is equal to what? Well, gamma on E lambda is lambda times the identity. Okay. Here there is an index I. Okay. There is an index alpha here. Okay. So what is this? This is lambda times a 2 by 2 matrix, okay, minus sigma 3 half times Qi E lambda. Why is there a 2 by 2 matrix? Because this guy here, this vector here, has an index alpha. We are acting on it by means of, so this is the result. And what does this mean? Well, it means that Q1I on E lambda modulo normalization factor, that gives us E lambda minus 1/2. Huh? Q2I E lambda, that gives us E lambda plus 1/2. So Q1I lowers the helicity by 1/2. Q2I raises the helicity by 1/2. Okay? So Q1I lowers, Q2I raises. Similarly, Q bar 1 dot I raises, Q2 dot I bar lowers. Okay? The other way around. Okay. So, now we are interested in massless representations. We are going to set the central charge to be 0. Why? Do we have a massless representation with central charge? No, but we are going to see this later. Okay? We're going to see this. We are going to see later on that if particle has 0 mass, there cannot be central charges. So Zij equals 0. We're going to motivate this choice later on. Then what we have is Q alpha I, Q bar alpha dot j. This is equal to 2 delta ij sigma bar mu p bar mu, okay, alpha alpha dot. And what is this? You just plug in, so it's not sigma bar, sorry, it's just p bar. Okay, you plug in the value of p, okay, in our reference frame, and what we end up with is twice delta ij E 1 minus sigma 3. Okay? 1 minus sigma 3. Here we have replaced the operator by its expectation value on any state, because all states in our representation have the same for momentum, because we are in S naught. As long as we are in S naught, for momentum can be replaced by this standard reference value. Okay. But what does this mean? Well, clearly Q equals Q bar, and equals 0 because Zij is 0. Okay. What does this imply? Well, this implies that Q1i, Q1 bullet I is equal to 0. Is equal to 0. Because the one component, okay, here has 0. There is a 0 eigenvalue of this matrix. Okay. Okay, is 0, while Q2i, Q2 bullet j, that's equal to 4 E, 4E delta ij. I guess it's 2E delta ij. Okay, it's 2E delta ij. Is it true? 4 or 2? 4? 4. I trust you. Okay. Very good. Then, what does this mean? This means that, remember, since this is the driver of this, these operators are simply 0 on any states in S naught. They're simply 0. They vanish. Because on any state, this implies that Q1i A plus Q bar 1 bullet I A squared, that is equal to 0. Okay? But this implies that Q1i A is equal to Q bar 1 bar A, and that's equal to 0. So all states are annihilated by the first component of Q's. Okay? First component of Q are simply not there. And so they are not effective in generating states on a given state. Okay? We will just set them to 0. We are left with the other. Define Qi as 1 over twice square root of E. Remember, E is non-negative. Times Q2i. Okay? Just define these generators, right? And they satisfy the following anti-commutation relations. Qi, Q bar j, Qrj, that's equal to delta ij. Okay? So in S naught, in our reference frame, supersymmetry algebra simplifies. It can be written in this form here. But this, what is this? This is the Clifford algebra of n fermionic degrees of freedom. That is the Clifford algebra satisfied by the creation and annihilation operators of free fermion fields, n free fermion fields. Okay? And how do we construct irreducible representations of this Clifford algebra? That's standard in mathematics, okay, we start from a unique Clifford ground state. Unique Clifford ground state. That is E lambda naught ground state, okay, characterized by the property that Qi E lambda naught is equal to 0. Okay? Okay. So then all the other states are all the states of the system in S naught are obtained by acting on this state by means of the other generators, Q bar. Okay? Remember that Q bar I lowers lambda. Okay? So generic state is obtained by acting on the ground state by means of Q bar. Okay? Q bar. And Q bar lowers lambda. Okay? So we start from E lambda naught. Then we have another, the first state is Q bar I acting on E lambda naught. Okay? And this is going to be E lambda naught minus 1/2 I. How many of these states do we have? As many as the generators I, so n. N. Then next are Qi, Q bar j acting on E lambda naught. That gives you E lambda naught minus 1 Ij. What do we mean by Ij in square bracket? Means that it is anti-symmetric in Ij. Okay? Anti-symmetric because these two anti-commute. These two anti-commute. So this state depends on I and j, okay, because it depends on which of these I use to act on the ground state, okay, but depends on the couple of index, okay, in this way, it's anti-symmetric in Ij, okay. So you see that this belongs to a representation of the R-symmetry group. Remember that with respect to the R-symmetry group, the index I spans the fundamental representation, the n representation of Un. Remember, GR equals to Un, automorphism group, okay? I spans a representation n of Un. The anti-symmetric couple Ij spans the representation n wedge n, okay, of Un. In Young tableau language, this is this representation here. Well, this is simply the square. We can go on and construct all the others. In particular, the generic state obtained in this way by acting on the ground state by means of K okay, of these generators Q bar, okay, this is E lambda naught minus K over 2, and depends on is totally anti-symmetric in the indices I1, Ik. So it belongs to the representation n wedge n wedge n k times, which is which corresponds to this Young tableau with n cells, n squares. Okay? Okay. Clearly, how many can I Well, first of all, how many of these states are there for each value of k? Number of states is clearly n over k. For each value of k, number k of generators, q bar acting on the ground state, I have n over k binomial. Okay, so the maximum number of q generators I can apply clearly is n. The moment I apply n plus 1, okay, I'm going to multiply two equal n q's together. But q's anti-commute, therefore they are unimportant. If I square any of the q's, I get 0. So the lowest helicity state is qi1, qin, or if you want q1, qn, e lambda naught, and that is equal to e lambda naught minus n half. Times what? Times a singlet, because here I would get an antisymmetric combination of n indices, which is a singlet with respect to un. Okay. Well, sun actually. Okay, with respect to sun. Now, so this is the lowest we can get, starting from the ground state and lowering the helicity by means of q bar. Okay, now there is an issue here about CPT. Remember, any local field theory is CPT invariant. Field theory, which is Lorentz invariant, is CPT invariant. This is the CPT theorem. Okay? Now, how does CPT act on helicities? CPT, in general, acts on a fermion by mapping it to some phase times chi star. This is the action of CPT on a fermion. On a fermion generator, you have a dagger instead of a star. Okay? And in particular, it maps qi, q bar I into qi. Okay. And moreover, it also maps helicity lambda into minus lambda. Helicity is odd with respect to CPT. Now, what does the CPT theorem imply in our analysis? First of all, since the theory has to be CPT invariant, an irreducible representation of a symmetry group, okay, has to be invariant with respect to CPT. This means that it has to contain CPT conjugate states. Okay? This means it has to be invariant. It means that the CPT transformation has to map the carrier of the representation into itself. The states of our irreducible representation into states of the same space. Okay? So the states of our irreducible representation should contain CPT conjugate. Okay, the space of our irreducible representation should contain CPT conjugate states. So for each helicity, it should contain the opposite one. This means that the carrier of the representation has to be invariant with respect to CPT. Doesn't mean that each state is invariant, but each state is mapped by means of CPT into another state of the same space. Okay? Good. This means that if we have an helicity here, we should have also the opposite one. And in particular, if the representation contains the ground state E lambda naught, it should also contain CPT conjugate. If it contains qi e lambda naught, it should contain also qi e minus lambda naught, and so on. Okay? So, besides these states which we have just constructed, CPT theorem tells us that our representation should also accommodate the CPT conjugate. So if we start from E lambda naught, we apply Q bar I, we get Q bar I E lambda naught, and so on. Okay? Then we have to start also from E minus lambda naught, the CPT conjugate, to the ground state, and act on it by means of Qi. And so on. Okay? So our representation space in S0 should contain two arrows of states. One obtained starting from the ground state and acting by means of Q bar on it. Okay? The other array is obtained by acting on E minus lambda naught by means of the Qs. Okay? So we get two arrays of states. Two arrays of states. So lambda naught minus 1/2, and so on, acting on Q bar by means of Q bar, then minus lambda naught plus 1/2, acting by means of Q. Okay? These are the representations. Well, this is the general structure of the representation. Example. Let me give you an example, and then I end here and up here for today. Example. Consider the n equal 1 Wess-Zumino multiplet. In this case, we choose lambda naught equal 1/2. Okay? Lambda naught equal 1/2. 1/2, 0, acting by means of Q bar. 1/2 minus 1/2, 0, acting by means of Q. Okay? So how many states does our representation contain? We have two helicity states, the two helicity states of a massless spin 1/2 field, plus and minus 1/2, and two scalars. Scalars do not have helicity states. Okay? So this can be written as 1 times 1/2 plus 2 times 0. Where in this notation, okay, using bracket, we mean the two helicity states. Okay, so when we write in round brackets a spin, okay, we refer to the two helicity states of the spin, plus and minus 1/2. So this clearly defines a spin 1/2 massless particle. So the representation contains a spin 1/2 massless particle with its two helicity states and two scalar fields. This is the Wess-Zumino multiplet. You see that the bosonic and fermionic degrees of freedom coincide. We have the two helicity states for defining the on-shell degrees of freedom of the spinor, of the spin 1/2 particle, 2 fermionic plus 2 bosonic. The degrees of freedom match on-shell. They don't match off-shell. But we are constructing on-shell states. They don't match off-shell because off-shell a spin 1/2 particle, okay, has 4 degrees of freedom. Well, here we have just 2 bosonic. The off-shell matching of degrees of freedom requires us to add a new field. a complex field, which is called auxiliary fields. We don't see auxiliary fields here, because here we just work on shell, okay? Okay, let's stop here for today. We'll go on tomorrow. Any question? Thank you. Thanks. Is there any question, by the way? No question. I stop.